In this video, you're going to learn how to code a deep queue network in TensorFlow 2 from scratch. No prior experience needed. You don't need to know anything about reinforcement learning. You just have to follow along. Let's get started. So before we begin, a couple of announcements. First of all, I put out a tweet on Twitter yesterday, one of the rare times I actually logged in, but the TensorFlow 2 implementation is significantly slower than the TensorFlow 1 implementation. I have debugged the issue and figured out why, but it is quite annoying and it will be the subject of a future video. Second point is I'm not going to explain a whole lot as we go along, just enough to get the gist of what we're doing. If you want to know the intimate details of how deep Q learning works, then you really want to check out my new course, Deep Q Learning from Paper to Code, on sale right now. But enough of that, let's get started. So here we are in our handy dandy file, and as I said, we're just going to go through this relatively quickly. So the basic idea is that deep Q learning is a temporal difference based off policy model free bootstrapped learning method, and the main innovation of the best implementation, shall we say, of deep Q learning utilizes both a target network and a replay memory. In this video, we're only going to use the replay memory. If you want to know why both are necessary for optimal performance, please check out my course. But for now, suffice it to say, we're going to do just the replay memory. But you're going to see that that is sufficient for the lunar lander environment. We begin, as always, with our imports. And we want to import keras as well. So our first class is going to be a replay buffer, and our initializer is going to take a max memory size and the input dimensions as input. So we want a max mem size, so we'll save that as a variable, and we also want a mem counter. Now the memory counter keeps track of the position of our first unsaved memory, and so we use that to insert new memories into the replay buffer. When the replay buffer becomes full, then the agent simply goes back to the beginning and starts rewriting its earliest memories. And we're going to represent the memory as a set of NumPy arrays. And the first thing we have is our state memory. This keeps track of the initial states the agent sees with each time step. And it'll have shape memory size by star input shape. So if that should be input dims, sorry. If you're not familiar with that idiom star something, it means to unpack in Python. So if input dims is a list, it will unpack the elements in the list. It's just a way of making it somewhat extensible in the future. And of course, we need a memory for the state transition so we can see, so the agent can remember what states it encountered next. And that'll also have the type np float 32. And we need a memory for actions. And that'll just be shape memory size because it's an integer. And we will use np int 32. Now this is for maximum flexibility with respect to the frameworks we want to use, and the reason is that PiTorch is quite particular about the data type here, as well as with the terminal memory, which we'll get to in a second. I'm actually going to probably redo my PiTorch video because the way I did it initially was with a one-hot encoding of the actions, and then I go back to an integer representation. It's really an ugly implementation, and I'm not quite happy with it, so I'll probably redo it. And that will also serve as a basis for comparison with TensorFlow 1, TensorFlow 2, to see that PiTorch is indeed the supreme champion of speed, which in my mind is the most important thing for deep learning applications. We also need a reward memory, and that is of shape mem size, and that will be float 32 because those can be floating point numbers. And we need a terminal memory as well, and that gets shape memory size by np int 32. Now the point of the terminal memory is to keep track of our done flags. The reason that is important is because the value of the terminal state is identically 0. Our next function is to add a transition to the memory buffer. So that takes a state, action, reward, new state, and done flag as input. And the first thing we need to know is what is the index of our first unoccupied memory. And we get that by taking the modulus, not the ampersand, of mem counter with mem size. And then we simply insert the states and variables at the appropriate point of their respective arrays. Good grief equals state actino. That's not right. And so I have 1 minus int done, and that is because when the episode is done, then the done flag is true. And so you want to multiply the reward for the terminal state by 0. So it has to be 1 minus done. You can also handle it in the learn function. It doesn't matter. I just leave it here for, that's how I like to do it. And then, of course, finally, you want to increment your mem counter, so that way you know that you've stored a memory. Next, we need a function to sample the memory buffer. And that takes a batch size as input. So we want to know what the problem we have to deal with now is if we haven't quite filled up the agent's memory, should we sample it? Answer is no, but we do, and we'll handle that in the learn function, but here we have to handle the question of have we filled up the agent's memory or not? If we have filled it up, then we want to sample that full length of the memory, and if we haven't, we only want to sample all the way up to the mem counter. And the reason is that we don't want to sample a bunch of zeros, because that doesn't tell our agent anything useful about the landscape of the, action value function. And so that's going to be given by the minimum of the mem counter, and the mem size, not the max, the min. And then we want the batch, which is a random choice, up to max mem unshape batch size, and replace equals false. And so replace equals false means that once we select a memory, we won't select it again. It gets taken out of the pool of random choice. So then we just sample the memory. States underscore and rewards actions and then return those quantities. States, actions, rewards, new states, and terminal. Okay, so that is it for our first class. That is our agent's memory. It is pretty straightforward. It's just a buffer to keep track of the state, action, reward, new state, and done flag transitions. So the next thing we need is a function to build our DQN. In the PiTorch implementation, we'll use a class, but here we'll just use a function. So we'll say def build DQN, and that'll take a learning rate, number of actions, input dims, and number of dimensions for our first and second fully connected layers as input. And we're going to build a keras sequential model that takes a list of stuff, in this case layers, keras.layers.dense, sc1 dims, and a ReLU activation. And then we need another dense layer, sc2 dims, activation equals ReLU. And then we need a final output layer. That takes n actions as output with no activation. All right. So that, I believe I have forgotten. There we go. So that is our build DQN. So now we want to compile our model with an atom optimizer, loss of mean squared error. Need that in quotes. All right. And one thing before we move on I want to change is from keras.optimizers import atom. I want to import atom, and I want to pass in the learning rate. So I've changed my mind on this implementation. Learning rate equals LR. I believe it's learning rate. Let me double check with the documentation really quick. Yeah, it's learning rate equals LR, and then loss equals mean squared error. And then we want to return our model. Okay, so that's it for our model. Next thing we want to handle is the agent class itself. So the agent class houses the memory, the network, as well as all the associated hyperparameters for our agent. If you wonder why I structured it this way, it's just to be consistent with the principles of object-oriented programming. An agent is not a deep queue network, but an agent has a deep queue network. Can I scroll down a bit? Let's do that. So our initializer is going to take a whole bunch of stuff: a learning rate, a gamma, number of actions, an initial epsilon, a batch size, input dims, an epsilon decrement, and we need some way of decreasing epsilon, which is the agent's proportion of the time that it takes random actions to solve the explore-exploit dilemma. And so we're going to decay epsilon over time by 1 by 10 to the minus 3. And we need an end value for that of 0.01. If you want to know why we don't go down to 0, I reveal that in my course. A memory size of 1,000,000 transitions, and a file name for model saving. Always important. So then we want to create the action space, just a list, and actions, and that is to facilitate selecting of random actions. So we'll also need the gamma, the epsilon. We'll also need the epsilon min, and that is epsilon end. We need a batch size, without a comma preferably. We need a model file, and that's fname. We need a memory, and that's a replay buffer object with mem size and input dims as input. We need the queue eval network, build dqn, that takes learning rate and actions, input dims, and we'll say 256 by 256 as input. Now you can pass it in as a hyperparameter to your agent if you so choose. I'm just going to default to something small because it seems to work relatively well. Next, we need an interface function between the agent and its memory. Kind of silly, but that's just kind of what you end up with when you deal with object-oriented programming. You end up with all these interface functions. Whatever. State, action, reward, new state, and done. This will say self.memory.store transition, state, action, reward, new state, and done. Okay, that's pretty straightforward. Next, we handle the functionality for choosing an action. So we say choose action, and that takes the observation of the environment as input. So if our random number is less than epsilon, then action is a random choice self.action space. Otherwise, if it's greater than or equal to epsilon, then we want to we want to basically add a dimension to our observation vector, and that's to deal with the sizing of the deep neural network. We have to pass it in a batch size basically, so 1 by 8. 8 is the number of observation elements for the lunar lander environment, instead of just passing in the observation itself. That's to accommodate passing in the batch of states at the end for our learning. Then we say actions equals self.queueval.predict state, and the specific action is going to be argmax of actions because we want to take a purely greedy action. No matter how we choose it, we need to return that action. Now, it is actually this function, oddly enough, in TensorFlow 2 that is incredibly slow. In fact, it is the inference rather than the training that is slow, and I can't wrap my mind around that. That doesn't make any type of sense. I have done a a full reinstall of Anaconda and Python and TensorFlow and all that good stuff, and it's still the case. So I don't think it's configuration specific. I think that is simply a bug in Google's implementation of their own framework. That wouldn't be the first time Google has bugs and stuff, if you know what I mean. But I digress. Next, we have a learning function. And as I alluded to when I was coding up the memory, we don't want to perform learning if we haven't filled up at least batch size of memories. So if we haven't, then we just return. Otherwise, we say states, actions, rewards, new states, and dones equals self.memory.sample buffer, and we pass in our batch size. So then we need to get the values for our temporal difference learning update, and we do that by passing the states and new states through the evaluation network. If we were using a target network, then that would come into play here, but we're not, so we're just going to use the evaluation network. So we want to get the value of the states and the new states, and then we want to create our target value. So the target is the direction in which we want our updates to move. So what we're really doing is we are updating the agent's estimate for the action value function, which is this Q. The name QLearning comes from that. And we are creating a target which tells the network the direction in which you want to move the weights to shift its estimates towards that quantity, the target. And the target, this eventually converges relatively well in most cases on the correct value. Not always, it's not guaranteed for the deep neural network case. So we'll say qtarget equals np.copy qeval, and we need to do this because of the way that assignment works in Python. So we want to copy, we don't want to actually change the values of both arrays when we do the next statement. So we have a batch index, and that's np range self.batch size d type np int 32. So this handles the array indexing. We have to do this because of how NumPy handles array indexing. So we say qtarget batch index actions. So for each state in our batch, for the action we actually took, we want to update that by rewards plus self.gamma times np.max qnext axis equals 1 times dones. So what we're doing is we are updating the qtarget value for the actions the agent actually took with this quantity, rewards plus gamma times the maximal action for the next state, multiplied by the done flag because the value of the terminal state is identically 0. And so now we want to do our training. So we'll say self.qeval.train on batch, pass in the states and the qtarget. And so this will recompute the predict for the states and then take the delta between the output of that feed forward, the predict, and the qtarget. And so the delta for the actions the agent did not take will be 0, and the delta for the action the agent actually took will be maximal. It'll be precisely what we want, which is our target value. So then we say we're done with the training. Basically, that's all there is to it. So we say self.epsilon equals self.epsilon minus epsilon decrement if self.epsilon is greater than self.eps min, else self.eps min. So that handles our epsilon decrement. You can do it by multiplication, by dividing by something. I'm just doing a straight linear decrement. It's not really critical for something like this. And indeed, it's not really critical at all, so don't lose too much sleep over it. Next, I want to give you a couple more functions. We want to be able to save and load models. And that's just in case you want to apply this to a little bit more difficult problems. So we'll say self.qeval.save, self.model file. Let me scroll down a bit, and then the next function we need is one to load models. So def load model self.qeval equals load model self.model file. So that tells me also that I forgot to import something. So we should do that now. And that is, of course, all the way up here. Sorry, I had to look at the documentation for a second. Keras.models import load model. Okay, so we have our optimizer and that, and that. Okay, so it looks like we have everything we need. So let's go ahead and right quit here. Oop, that's not what I wanted to do. Hit escape, then right quit. Now we want to do our main loop. So we'll vim main tf2 simple, yeah, dqn lunar lander. So we start with our imports from simple dqn tf2 import agent, import numpy as np, and we'll need that to do our averaging of the previous 100 games. We'll need Gym to handle our environment. From utils import, I'll have to double check the name on this, plot learning curve, and this is my custom plotting function. If you don't know where this is, just do a git clone of my directory. And then we want to import TensorFlow as TF. Now this is where the solution to TensorFlow's jankiness comes into play. So we'll say if name equals main, then the first thing I want to do is I want to turn off eager execution. That is right. tf.compat.v1.disable eager execution. And this is one of the core functions of TensorFlow 2, and it is slow as molasses. This thing is incredibly slow. It's in fact almost an order of magnitude slower than TensorFlow 1, and it's still a good 60 to 100% slower than PiTorch, something like that. I haven't benchmarked it against PiTorch, but it feels significantly slower. And the source of the slowness, the source of the jank, comes from the predict function, and I will prove that in my next video because this really annoys me. I don't know why you would sacrifice execution speed, particularly for inference. That makes no sense whatsoever, but nonetheless, they did. So we'll say env equals gym.make lunar lander -v2, and we'll set our learning rate to 001, number of games 500, agent equals agent, gamma 0.99, and epsilon of 1, learning rate of learning rate, input dims equals env.observation space .shape sub 0, and then I probably want to put that on a new line because we are violating the PEP 8 style guide. And then we want to say and actions equals env.action space .n, I believe, and then mem size equals 1 million, and batch size of 64, and epsilon end of 0.01. We need an empty list to keep track of our scores, an empty list to keep track of our epsilon history. That's so we can see how the agent's score evolves over time as a function of its decreasing epsilon. And then we need to player number of games for I in range n games. Done equals false. We want to reset the done flag at the top of every episode. Score equals 0. Observation equals env reset. While not done, action equals agent dot choose action. Observation underscore, which is the new state, reward not reared, reward done info equals env step, score plus equals reward. We want to keep track of our total score for the episode, and storing our transition at each time step, observation action reward observation underscore and the done flag. And then we want to set the current state to the new state. So that way, the reason we do that is so that at the next iteration of the loop, we are choosing an action based on the current state of the environment because it is shifted from observation to observation underscore. And we also want to learn with each iteration. That's what makes it temporal difference learning. And then we want to append our agent epsilon to the epsilon history and the score array. We want to append the score. Calculate our average score, MP mean scores max 0I minus, let's just do MP mean scores minus 100. And then say print episode I score to F score average score and for grins let's say epsilon. File name equals lunar lander tf2.png, and then we'll say this is just for my plot learning function. X equals I plus 1. That's for our x-axis. I in range and games. Plot learning curve x scores eps history file name. All right, so that looks about correct. So let me right quit, and then the first thing I want to do is check this out, and right away I see it is plot learning, not plot learning curve. I've changed the name over time. So let's go back to main tf2 and come back here and just change the name just to be consistent, because there's nothing worse than getting all the way to the end and realizing that you have called it the wrong thing. Learning curve. Is that right? Let's see. Plot learning curve. No, it's plot learning, of course. Plot learning. I am tired. And we get rid of this. At least I'm not so tired that I didn't know it was wrong. All right, now moment of truth. Let's see how many typos I made. So Python main tf2. No module named keras. Okay. And of course, this is because we're dealing with TensorFlow 2 and not vanilla keras. So let's just do this. We will say vim simple tf2.py, and we come here. And actually, do I need this? Do I reference keras? I do keras.sequential, so we'll do this then. Input TensorFlow dot and TensorFlow dot, and that should take care of it. And we'll move on to the next error. Name mem size is not defined. Okay, so that is line 9. So right here, mem size equals max size. Simple enough. And so it is telling me int object is not iterable. What this means is that I'm passing it an integer instead of a list. So let's come back to the main file. And we don't want to pass in the 0th element of the shape. We want to pass in the shape itself. I believe that is correct. Let's try it again. Agent object has no attribute action space. That must be a typo. We want to go to here. That is in the agent class. Self.action space. Insert space. Escape. Right quit. Try it again. Agent object has no attribute epsilon dec. Okay. That is down here, and that is because I did not save it. Epsilon decrement. Epsilon decrement. All right. Try it again. Oh, interesting. So it says X and Y must have same first dimension but have shapes 501. So that is interesting. So that means it fell through. Okay. It reached the plot learning function really quickly. So that means there's something wrong in the main file. So endgames equals 500. Done equals false. That's interesting. Oh, that's why, because I have an extra indent here. What is it? Shift. No, that's not it. There we go. That's unindent. Right, quit. Oh, but I'm still going to have... Oh, because it only played one game. That's why. So that should be fine when it finishes. Okay, now it is learning. So I'm going to let this ride for a minute, and we'll come back in a little bit, and you'll see how it did. All right, and we are back. Now, this took about 40 minutes. I've already worked on the script for my next course, as well as started editing the video for this particular video. So this took way too long, but you can see it has finished. And I'm going to show you the plot here. You can see that the agent starts out not knowing anything about the environment, which one would expect. That is perfectly normal. And the performance kind of oscillates, but comes with an upward trend over time. And one thing that's really interesting is you notice that the agent does the vast majority of its learning after the epsilon has gone to its minimum value. And so it's not, that's why I said it's not really critical how you decrement epsilon over time, because most of the learning happens, you know, when the agent is on its most agreed mode of operation anyway. But you can see we have an average score hovering around 200 or so, which is good enough to call it solved for the environment. Now, of course, we would need an extra innovation to apply this deep neural network to more advanced environments, such as a target network, but that is a topic for a future video. So if this was helpful to you, please leave a like, a comment, and subscribe. Hit the bell icon so you don't miss my next video, which will be on the the performance comparison between TF2, TF1, and PiTorch implementations of deep Q learning, because that is quite interesting. Something that rather shocked me. I didn't expect TF2 to be so friggin' slow. It's really quite a disappointment. Anyway, I look forward to seeing you in that next video. Oh, but before you go, real quick reminder, my new course, Deep Q Learning From Paper to Code, is on sale on Udemy for $9.99. Pick it up for the next few days using the link in the description, not the pinned comment, the description. See you in the next video.